In this video, we're going to go over section 11.3 from our textbook, which is on vectors. So first, we're going to start with some basic terminology of vectors. Starting here, a scalar is what's known as just a magnitude. So for example, 45 pounds would just be a scalar. Now, a vector quantity is going to be a magnitude along with a direction. So for example here, 50 miles per hour in the east direction. So, for example, here, this vector has a magnitude of 10 pounds, and then our direction is going to be 30 degrees from our horizontal here. Now, vectors are denoted in bold or with an arrow over the letters. So, for example, OP here or OP with this arrow, that represents the vector OP. This brings us to this vector. So when we're writing vectors like this, the first letter is going to represent the initial point. So for example, this is the vector OP here. We start at O, we end at P. The second letter is going to be our terminal point. Now the vector OP and PO are not going to be the same vectors. As we can see here, we're starting at O and terminating at P. This is our vector. Now in this case, PO would be starting at P and terminating at O. And remember, direction is important with these vectors. These guys have the same magnitude, but in opposite directions, as we can see with these two arrows there. All right. Vectors are also going to be commutative. So if we're adding A plus B, this is the same as B plus A. And the sum of our vectors A and B is going to be the resultant of A and B. Also, for every vector V, there's going to be a vector minus V, such that we have this here, and that's called the zero vector. Now lastly, the scalar product of a real number, so we have a scalar k and a vector u, is just going to be this here, which has magnitude the absolute value of k times the magnitude of u. Now if k is going to be less than 0, then k times u is going to be in the opposite direction as u. So here are some examples here. If we have this vector u, then 2 times u, so in this case our scalar k is going to be 2. That's going to be double the size of this guy, double the magnitude of u. Similarly, for 3 over 2u, this is going to be 3 halves of u. This will be 1 half of u. And in this case here, we have minus 2u. This will double the size of our original vector u, but it will also turn the vector in the opposite direction. As we can see here, k is going to be less than 0. It's going to be minus 2. So our vector u is now in the opposite direction of this guy. All right. Now we're going to move on to our interpretation of vectors here. So a vector with its initial point at the origin is going to be called a position vector. Now a position vector u with endpoint a comma b here is going to be written as this here, where a is going to be the horizontal component and b is the vertical component of u. Now the horizontal and vertical components of this vector u, having this magnitude here and direction, so we'll get to that in a moment, are given by this here. So a, our horizontal component, is going to be the magnitude of our vector u times cosine of our angle theta. And similarly for our vertical component here, this will be the magnitude of our vector u times sine of our direction angle theta. So let's look at this example here. We want to write this vector in this form here, just given this guy. So I kind of drew it on the side here to kind of blow it up. This picture was very small, but what we're given in this case is this vector u. We're given a magnitude of 4, and then the direction is going to be 70 degrees from this horizontal here. Now remember, our a component is going to be our horizontal component, and then b is going to be our vertical component here. So that's how we can think of what's going on here. Now in this case, if we want to write our vector in this form, we can just use this guy here. So u is going to be given by our horizontal component and our vertical component. Now we know our horizontal component a is going to be the magnitude of u times cosine of our given angle. Now the magnitude of this vector u is 4, So this will be 4 times cosine of our direction angle, which is 70 degrees. And similarly for B, that'll be the magnitude of u times sine of our direction angle theta here. All right, and then putting this into a calculator and evaluating these guys, we'll get roughly this here for our horizontal and vertical components. So this one here is our horizontal component, and this guy here is our vertical. All right, so this brings us to our vector operations. So if we have this vector u here, where a1 is going to be our horizontal component and a2 is our vertical component, then minus u just turns this vector in the opposite direction. So that makes sense that our horizontal component and our vertical component will now be in the opposite directions. Also, if we were to multiply this vector by a scalar k, then this k is going to alter our horizontal and our vertical directions by the magnitude of this scalar k here. Additionally, if we have a, b, c, and d, and k just represent real numbers, if we were to add two vectors here, a, comma b, and c, comma d, what we're doing in this case is we're adding our horizontal components, so this a plus c here, and then we're adding our vertical components b plus d here separately. So we end up with this resulting vector, which is the sum of our horizontal and vertical components. Similarly, for subtracting two vectors here, what we're going to do in this case is we're going to subtract our horizontal components and our vertical components. So this resulting vector here is going to be the difference of our horizontal and our vertical components separately. So let's look at an example of this. In this case, we're given these two vectors, u and v, and we want to find these guys here. So for part A here, we're starting with 7u. So we're multiplying this vector u by a scalar 7. So this will be 7 times this vector here. And as we saw up here, this scalar component is going to be multiplying our horizontal and our vertical components, a and b. So this will be 7 times 2 will be 14. That's our new horizontal component. And then 7 times 8 will be 56. That's our new vertical component. All right, let's do part B here. So we have 7 times u plus 3 times v. In this case, v is 4, 0. Now we saw from part A that this first part, 7 times u, is going to be 14, 56. Now for this next part here, again, we are multiplying the scalar to both our horizontal and vertical components. So here we'll get 12, 0. Now what we want to do is add these guys. So we're going to use this here. When we're adding these two vectors, we're going to add our horizontal and then our vertical components separately. So here we'll have 14 plus 12, and then 56 plus 0 for our vertical component. This will give us 26, and 56 is our resulting vector from doing these operations on these two vectors here. All right, and lastly, let's look at C here. We have v minus 3u, so v is 4, 0 here. We're subtracting 3 times our vector u. So we still have this first vector v here, and then our second term here, this 3 times our vector u, is going to become 6 times 24. Now we want to subtract these guys, so we're going to subtract our horizontal and vertical components separately. So we'll have 4 minus 6, and then 0 minus 24. And then our resulting vector will then be minus 2 minus 24. All right, so this brings us to our magnitude and direction angle of a vector. So the magnitude, or the length of our vector, is going to be given by this guy here. It's going to be given by the square root of our horizontal component squared plus our vertical component squared. And then the direction angle theta satisfies this here, where we're not going to be dividing by 0. So let's look at this example here. We want to find the magnitude and the positive direction angle for our vector u. example, finding the magnitude, we'll just plug this into this guy up here. So this will be the square root of 5 squared plus negative 12 squared. This ends up being the square root of 25 plus 144, which is going to be the square root of 169, which will be 13. So the magnitude of this vector is going to be 13. Now we know the direction angle satisfies this here. So this tells us that tangent of our direction angle is going to be equal to negative 12 over 5. Getting this angle by itself, we'll take arctan on both sides. And then plugging this into our calculator, we're going to get roughly minus 67.38. Now notice, I have this guy here, so we can kind of visualize what's going on. We know our horizontal component is going to be 5. So moving in this direction, we have length 5. And then our vertical component is going to be minus 12. So we're moving in this direction, minus 12 here. Now, if our direction angle here is going to be minus 67.38, then our vector is going to look something like this here, where this angle theta is going to be minus 67.38. However, in the question, notice that we asked for the positive direction angle for u. So in this case, we just want to figure out what this angle is here, starting from the horizontal going to this vector here. This will be u. So what we can do is add one full rotation of our unit circle. So this positive direction angle will then be minus 67.38 plus 360 degrees. So all degrees here. So we're just doing one full rotation. We'll end up at the same magnitude and direction here when we do that. So adding this, we get 292.62 degrees. All right, so this brings us to some more terminology on vectors. So first, two vectors are going to be equal if and only if they both have the same magnitude and direction. Also, if we want to find the sum of two vectors, let's call A and B, we can do either one of these things here. The first being that we'll place the initial point of B at the terminal point of A. So these two vectors coinciding right here. Then the vector with the same initial point as A, so right around here, and the same terminal point at B is going to be the sum of these vectors, A plus B here. Or we can use what's called the parallelogram rule. So we'll place the vectors so that their initial points coincide here, so A and B. Then we'll complete the parallelogram as shown here. So the resulting vector is going to be this A plus B here, and this is our parallelogram. And notice we end up with two right triangles here. So we can use that information to find the length of this guy. Now we'll do an example using this parallelogram rule, but first here are some properties of parallelograms. So this is listed here, and the one we'll use in this example is number 2 here. So the opposite sides of a parallelogram are equal, and the adjacent angles of a parallelogram are going to be supplementary. So we'll keep that in mind as we do this next example here. So we're going to use the parallelogram rule to find the magnitude of the resultant vector for these two forces shown in this figure. So what we want to do is draw a parallelogram, which will look like this here. Now if I call this our side A and this our side B, then this vector will be the sum of these guys, and then we can call this one C. Alright, so let's continue to label this. If this is going to be our side A here, then we can call this our angle A. We can call this guy our angle C. This would be our side C here. And then, since this is our side B, this is also B here, and then this can be our angle B. Alright, so the first thing we're going to do is use this property here. So the adjacent angles of a parallelogram are going to be supplementary. So the two adjacent angles that we're going to look at here are B and C. So this angle and this angle. If these guys are supplementary, this tells us that their sum is going to be equal to 180 degrees. So what we can do is use this information to find our angle C, because notice we're already given that our angle B here is 30 degrees. So our angle C is just going to be 180 degrees minus 30 degrees, which would be 150 degrees. So now, remember, we're trying to find this guy here, this side C. We have an angle C now. We also have a side A and a side B. This indicates that what we can use is the law of cosines to find our side length C here. Remember, the law of cosine tells us that C squared is going to be equal to A squared plus B squared minus 2AB times cosine of our angle C. So C squared is going to be equal to this here. And then plugging this into a calculator, this is going to be approximately this here. And then taking the square root of both sides, this tells us C is going to be approximately this guy here. So this is going to be the magnitude of this resultant here. All right, and then this brings us to the last thing we're going to talk about, which is a unit vector. So this is a special vector that has magnitude 1. And so two very useful unit vectors are defined as this here. So in this case, I is going to be equal to this. So our our horizontal component is going to be 1 and our vertical component is going to be 0. And then on the other hand, for j here, our horizontal component is going to be 0 and our vertical is going to be 1. So that looks like this here. So if we have a vector v that's equal to this here, then we can write our vector like this here, where a represents the magnitude of our horizontal and b represents the magnitude of our vertical components. So let's look at this example here. In this case, we're given vectors u and v written in this form. And what we want to do is find these guys here. And so I've already written this here. Our vector u is going to be 2i. So remember, I is going to be 1, 0 here. So this means we don't have a vertical component. So that's why we have 0 in this case for b. And on the other hand, our v is given by 9i. So that means our horizontal component is just going to be 9, and then plus 4j, so our vertical component is just going to be 4. So let's do part A here. We have 7 times u. And so in this case, if we wanted to write our answers just in terms of I and j's, this would just be 7 times 2i. This will be 14i, and this will be our final answer. Now for part B here, we have 7u, so we know that's already going to be 14i, and then plus 6v. So this will be 6 times our vector v here. So we'll have 14i here, plus, so this 6 here will be multiplied to both of these terms in our parentheses here. So this would be 54i plus 24j. And just like we saw with our vector operations when we were just looking at it in this form here, we're going to add our horizontal and our vertical components separately. Notice we have 2 horizontal components here and then just 1 vertical component here. So we will add our i's together, and we can think of this as combining like terms. So we'll just take 14i plus 54i, so this will be 68i, and then we have our 24j. And so this will be our final answer for this guy. And lastly, we have v minus 6u. So v is 9i plus 4j, and we're subtracting out 6 times u. So 6 times 2i. So this will be 9i plus 4j minus 12i. And again, we are going to add and we'll add and subtract our horizontal and vertical components separately. So in this case, we will have 9i minus 12i. So this will be minus 3i, and then we just have this 4j still. So this will be our final answer for this guy. Alright, so that'll be it for this video.